Great. Everybody, we are starting. Hope you have a wonderful morning. We are starting with a recap of what we have done last week, and it's Legendre transformation. In general, if you remember, we did it for energy, right? And the energy was a function of entropy, and it was a function of volume, and it was a function of the number of particles that we have inside. And the idea was, I don't really want to look on the entropy. I want to change my generalized variable, for example, to temperature, and how it's achieved. So the appropriate function is a Helmholtz free energy, which is a function of temperature, volume, and the number of particles. And what we have done, we performed the following transformation. F was equals to E minus Ts. So if you remember, instead of describing the behavior of the system in terms of, for example, y and x coordinates of a specific curve, we look on the derivative of the curve of the function at a specific point, and another point where the function or this derivative, tangential line to be more precise, crosses the y-axis. Okay, so this was the transformation. And when we perform this transformation, f indeed becomes a function of temperature, volume, and the number of particles. Now, if we look on the energy, and we know that dE equals to TdS minus PdV plus mu n, where mu is our chemical potential, this is a generalized force, minus P, or P is the pressure, which is also a generalized force, and T is a temperature. They're all generalized forces. They are not the variables of E. The variables of E are extensive variables, and those generalized forces are intensive variables. When we perform the transformation, the Legendre transformation, we obtain that dF equals to S dt, minus S dt minus P dV plus mu n. Okay. So from here, what we see that dF to dt equals minus S. The pressure stays still the same. dF to dV equals to minus P, and dF to dN equals to the chemical potential mu. Now, we can do this for any variable that we have in our energy, or in general for any function, right? So if we have function y, which is, let's call it function A, which is a function of x1 and x2 and x3, okay? And I don't really like coordinates x2 and x3. Legendre transformation tells us, well, you can use instead coordinates x2 and x3, some conjugated variables. And how do you find those variables? So first of all, you write down dA as dx1 plus dx2 plus dx3. In front of those guys, you have y1, y2, and y3. Okay. So write down your differential. The Legendre transformation tells us the following. You don't really like x2 and x3. Okay? So you define a function. You define a function b, which is going to be a, and for example, you want to swipe x2 and x3. Great. So you write it down a minus the conjugated variable that is associated with x2 is y2. Okay, so you write down y2, x2. And the conjugated variable that associated with x3 is y3. So you're writing down minus y3, x3. Now, b, your new function, is a function of x1 you left, so it stays the same, x2 you modified, and it's going to be y2, and x3 you also modified, so it's going to be y3. Okay. So this is your new function, and instead of x2 and x3, you got the conjugated variables. Now, in the original part, y1 was dA to dx1, and y2 was dA to dx2, and y3 was dA to dx3. When you perform this modification, what you have for the derivatives? So you write down dB. Right? So what is dB? It is dA minus y2 x2 minus y3 x3, which is dA minus d y2 x2 minus d y3 x3. We'll open up everything that we have, all the differentials. So first of all, dA, we know what dA is. It is this differential that depends on dx1, dx2, and dx3. So it is y1 dx1 plus y2 dx2 plus y3 dx3. We go to the next differential. So we have minus, and here is the differential of a multiplication of two functions. So we have y2 dx2 plus x2 dy2. Now we go to the third differential, which is, again, it is differential of multiplication of two functions. So we have y3 dx3 plus x3 dy3. Now we cancel everything that we can. So y1 dx1, it still stays. y2 dx2, here is a plus sign over here, here's a minus sign over here. So we'll cancel this out. Okay, now we have y3 dx3. Here we have minus y3 dx3, so we also cancel this out. Eventually, we're left with the following three terms. y1 dx1 plus, minus x2 dy2 minus x3 dy3. This is dV, which means, exactly as I wanted, b is a function of x1 and y2 and y3. But there is a little bit more to it. So since y1 stands in front of dy1, I know that y1 equals to what? To dB to dx1. Okay. I haven't modified it. It stays the same as over here. So y1 is dA to dx1. x1 wasn't modified to anything, to the conjugated variable. So the derivative stays the same. But look on the second derivative. So the derivative, so what we know, minus x2 equals to what? Since minus x2 stands in front of the differential of y2, it is dB to dy2. Okay. So notice dA to dx2 equals to plus y2, and dB to dy2 equals to minus x2. So the sign of the derivative is interchanged. If it was plus before, it's going to be minus after the transformation, after the Legendre transformation. The same goes for minus x3. So minus x3 equals to dB to dy3. Now you can extend this to as many variables as you want. Okay? So the Legendre transformation is a way to take a general function of many variables. It doesn't have to be one variable, two variables, three variables. as much as you like. Okay, you perform a you basically take out the variables that you don't want to use, for example x2, x3, and you obtain a new function, a function of your new conjugated variables. Why should you do that? Well, mainly because you don't want to use x2 and x3 and you want to use y2 and y3. Very, very, very convenient. Now, the moment that you do it, right, you obtain all these thermodynamical potentials that we have written before. Okay, so what kind of thermodynamical potentials we have written? Let me recap this too. So what we have is the following thermodynamical potentials. So we have F, it is E minus Ts, which is Helmholtz free energy. And since I taken minus, F is going to be a function of T and a function of V and a function of mu. I'm sorry, N. I have written several other thermodynamical potentials. So, for example, Gibbs free energy, G, and G is E minus Ts minus PV. So it will look as I'm adding plus PV, but it's just because the intensive variable or intensive force is minus P and not plus P. And this is Gibbs free energy. And so look, I modified S to T and I modified V to P. So it's going to be a function of T, P, and N. Okay. Also, another interesting thermodynamical potential is the grand canonical potential, which is E minus T S minus mu N. This is grand canonical potential. We'll see later why it's called like that. And we see that what we modified, S gone to T, N gone to mu. So it is a function of T, it's a function of V, and it's a function of mu. Now I haven't proved that, but as I have proved that the energy at equilibrium, it's at its minimum, okay? The same goes for all the other thermodynamical potentials, okay? It's a general statement. Any potential that is obtained by Legendre transformation from the energy, since energy at equilibrium at its minimum, it's an extremum point, the same holds for any other thermodynamical potential. Okay. Great. Now, there's sometimes raises a question of what all those potentials actually mean. Why should I use them at all? So, the first thing is, well, because it's convenient. Sometimes it's much more convenient to operate with other variables. The second answer is, well, sometimes I have more feeling or I want to modify or quantify some specific variable that is not extremely clear what it means when I'm operating with energy, but when I'm dealing with other potentials, it tells me exactly the thing that I want to measure. And the first example, well, let's look on the Gibbs free energy. Okay? I want to describe to you what Gibbs free energy actually means. Now for this, we will use some additional information about what happens to functions like energy and other thermodynamical potentials. Now, I want you to remember that the usual perspective of thermodynamics is that everything is described by some continuous functions, right? So we have a matter, we had some axioms about entropy, that from this it followed that there's properties of energies, etc., etc. And eventually everything is continuous. Okay? We will see what I mean by continuous. Okay? Now, so all the calculus of functions of many variables is applicable everything. So you modify one variable, you go from one state to another. Okay? And those values of those variables define exactly in which equilibrium state you are. Great. So everything that you know about functions of many variables is applicable over here. This is why when you study thermodynamics is sometimes looks a little bit awkward. So you do this and then you do that, you operate with some derivatives, you have those Maxwell relations if you remember from the class of Bina, etc., and then you get another equation. And you do this transformation or that transformation and then you get another transformation, another equation. But what exactly all of this means? Right? So I will try to describe it to you a little bit on the part of the Gibbs energy. So first of all, so we're going to use just the tools of calculus, right, to see a little bit of what different potentials means, focusing on the Gibbs free energy. So first of all, if you don't remember, I will remind you, there is something that is called homogeneous functions. Right. So this is physics or mathematics for physicists or calculus 101. So if g of lambda multiplied by x equals to lambda to the power n multiplied by g of x, g of x is homogeneous of order n. So if you remember different methods in ordinary differential equations, the moment that you have homogeneous functions there, a lot of that you can do in order to solve your ordinary differential equation. So, okay? Now this holds not only for one specific coordinate. If you have g of x1 and lambda x2 and lambda x3 and lambda xn, and it equals to lambda, let's call it larger, and it equals to lambda to the power of n of gx1, x2 to xn, g is a homogeneous function of order n. Great. Now, theirs was this guy, Euler, and he proved the following theorem. Right? So what Euler proved? Euler stated the following thing. Euler theorem for homogeneous functions. So let's assume that g of x1 to xn is homogeneous of order 1. What it means is that g lambda x1, lambda x2, lambda xn equals to lambda g of x1 to xn. Then g of x1 to xn, it can be written in the following form. I goes a summation from 1 to n, a partial derivative of dg dxi, xi. This is the Euler theorem. I won't prove it to you. Hopefully you've seen a proof of this or a sketch of proof of this once in your lifetime. But it's actually very useful in thermodynamics. Why it's useful in thermodynamics? It's useful in thermodynamics because energy is an extensive function. And it depends on extensive variables. Right? So what do we know? We know that T is a function of what? Of S, of V, and of N. Let's assume that I increase my system by a factor of lambda. Now, since I increased my system by a factor of lambda, the entropy is extensive, so it's also increased by a factor of lambda, right? So what happens to E of lambda S and lambda V and lambda N? That's the question. Is it homogeneous? Is it not homogeneous? Etc. etc. Now look on the differential. So the differential d of E equals to what? So now my variables are lambda S, lambda V, lambda N. So I have T d of lambda S minus P of d of lambda V plus mu of d of lambda N. So there is a transition that allowed me to go from this part, okay, writing the energy in such a form, to this part. And what is this assumption? The question is, if I increase my system by lambda, why nothing happens? So why all this affected only whatever stands in the differentials? Why it hasn't affected whatever stands in front of the differentials, right? And the answer is, well, it's my assumption of how exactly the differential of energy looks like. I know that those are extensive variables. Those are intensive quantities. They're not affected by the size of the system. Okay? This is why, by increasing everything by lambda, T stays the same, P stays the same, mu stays the same. It is a strong assumption about equilibrium and what is exactly the energy. Great. So d, E, when I modified everything by lambda, it is lambda T ds minus lambda P dV plus lambda mu dn, and it is solid E prime, right? Because E where I haven't increased it by lambda, and E prime when I increased it by lambda. So I just take lambda, and I have here TdS minus PdV plus mu dn. So this is lambda dE. I obtain that dE prime equals to lambda dE, meaning E prime equals to lambda E. Alright, so I have a homogeneous function. The energy is homogeneous function of order 1. I increased everything by lambda, and the function also increased by lambda. And the other theorem says that if I have a homogeneous function of order 1, okay, I can represent it in this form. So let's write it down. Now, this is actually the part of thermodynamics that I don't really like. Why? Because you work with functions, and then you obtain something. So there is no, how should I call it, ideology. It's not that I can see in the first place what I'm going to get. So it's a lot of games with calculus, and eventually get something and say, oh, I understand, I like this result. Why? Well, because I like it. So let's see. So according to Euler, what we obtain? We obtain the energy equals to dE to d. The first derivative is with respect to entropy. So we have dE ds multiplied by s. Right? This is our first variable. The second variable is plus dE to dV multiplied by v. The third variable, it is plus dE to dN multiplied by n. This is Euler theorem. What is dE to ds? What is dE to ds? Let's write it down over here. we know dE equals TdS minus PdV plus mu dN. Okay. The only thing that you always have to remember is what is the differential of the energy, okay, and how to perform Legendre transformation. That's basically all. So I write down the differential of the energy. I know exactly, okay, so those are my variables, and those are the partial derivatives. So whatever stands in front of ds is the partial derivative of E with respect to S. So instead of d to ds, I write down T. So I have Ts. Instead of d to dv, it is minus P. Minus P multiplied by V. And instead of dE to dN, I have mu plus mu multiplied by N. So this is the expression for energy that I have. Great. Well, how it's useful, why it's useful, why stop here? This is what I've told you. A lot of expressions, because you can apply a lot of different calculus rules and theorems, and sometimes some of them are useful, some of them are not really. So we have this guy. Great. Now, so in general, so this is the expression for energy. You remember I wanted to explain to you a little bit about Gibbs and what the properties of the different thermodynamical potentials. Okay, so if this is the expression for E, then let's write down what is dE, right? So what is dE? Is the differential of Ts minus PV plus mu N. Right? Now, from one side, I know what is dE. Right? This is dE. So I write it down like this. On the left-hand side, it is TdS minus PdV plus mu dN. Where from? Well, this is the regular expression for the differential of the energy. This is the first law of thermodynamics. The right-hand side is whatever I obtain from the second law of thermodynamics and assumptions about continuous representation of my functions, right? And the Legendre transformation, so a bunch of calculus. What we have here, it is d of Ts minus d of PV plus d of mu N. Okay. So let's open up all the parentheses. So dTs, it's again this game. The multiplication of two functions. S dt plus t ds. What is here? Minus d minus v dp minus p dv. And the last one is plus n d mu plus plus mu dn. Okay, so we have an expression of the left-hand side, a bunch of differentials and some variables, or let's call them forces, generalized forces. It's a modular expression with differentials on the right-hand side. Now we can cancel out a bunch of things. So TdS goes with TdS. Okay, minus PdV goes with minus PdV. Mu dN goes with mu dN. Great, so on the left-hand side, we canceled a lot of stuff. And on the right-hand side, we are left with that S dt minus V dp plus n d mu equals to 0. Okay, so you arrive to some equation, and if you're the first one to do it, it gets your name. Now there were two guys who derived it, so it's Gibbs, Duhem equation. You look on this and say, well, it's not really interesting, this Gibbs-Duhem equation. Why it's interesting? So it's an expression, fine. We'll actually see why exactly it's an interesting equation and why it should have this name, a specific name. But for being, we say, well, okay, we apply these calculus theorems, we arrive to something that doesn't seem really useful. Okay. Remember, my idea is to explain to you a little bit about thermodynamical equations or potentials. So it's about Gibbs. Gibbs. He also had this function, this thermodynamical potential. Remember, what is Gibbs? G. So G is E minus Ts minus PV. This is the Legendre transformation when instead of working with S, we work with T, and instead of working with V, we work with P. Okay. Now you look on this, you say G, it is E, and E, well, where is E? Is Ts minus PV plus Un. This is that. That's substituted inside. So we have Ts minus PV plus mu n. Okay? And here we have minus Ts plus PV, and that's it. So what we obtain for Gibbs, and that's related to this equation over here, that this thermodynamical potential, G, is simply mu multiplied by n. So remember, what is energy? Energy is something well described. There is heat, there is external work, etc., etc. Now we can work with some other thermodynamical potentials. Why? Well, there is a mathematical theory, this Legendre transformation. It's useful. It's useful. But it's not only useful. It depends on what you want to look on. So from this equation, what I understand that this thermodynamical potential, G, is basically saying to me that if I'll take this G and I divide it by the number of particles inside the system, I will get the chemical potential. So G describes to me by how much the energy of the system is increased when I add particles. That's it. Okay. So this is the meaning. And all the other different thermodynamical potentials have some meaning when you look on them. So it depends on what you want to look on and with what quantities you want to work. You want to work with chemical potentials, with adding particles, you work with Gibbs. You want to work with something else, you work with the appropriate Legendre transformation of your energy. So it's not just a mathematical trick. It's not just, well, it's convenient to work with this kind of coordinate or with that coordinate. There is also some sort of intuition behind every potential. It's not that somebody just described it and that's it. Oh, I have this main. I need to put my main on intuition. No, there is an intuition. Yes?
For every potential, you can find expression like this.
No, it's not always look so nice,
yeah.
Right? It's not always look so nice, but it describes something. It describes to you what is the actual change of energy you want to work with. Okay? Any other questions? No other questions. Great. So what I want to do now is two things. I don't have a lot of time, so let's do just the first one. And the thing is, well, we'll step away a little bit from calculus, etc., and we ask the following questions. Question: what are the properties of generalized forces in equilibrium? Okay. Now, we will use the trick that I already described to you, but first I will describe to you the question. So let's assume that my system, I can subdivide it to many other systems. So let's assume that this is my whole space, my system, my world. But it actually composed out of system A, system B, and system C. Okay. Now, And I want to ask the following question. I have generalized forces. What are my generalized forces? Temperature is a generalized force. Pressure is a generalized force. Chemical potential is a generalized force. Okay, some specific other magnetic momentum can be a generalized force, or average magnetic momentum. Now, my question is, for example, here I have T1, and I have T2, and I have T3. Okay. I have different temperatures, or I have temperature T1 for system A, temperature T2 for system B, and temperature T3 for system C. Now, the moment that I say to you the magic word, equilibrium, there is very harsh constraints on T1, T2, and T3, right? We saw already, if we take two systems, we make a contact between those two systems, we look for a while, we leave the system for a while, it equilibrates, then we know that the temperatures of two systems have to be exactly the same, right? Now, so if we extend this argument that we used already before, I would say the moment that I say that 3 systems, 4 systems, 5 systems are at equilibrium, the temperatures T1 and T2 and T3 are at equilibrium. Okay? Now, but it's actually the same argument can be extended to any other intensive variable. So if I have here P1 and have here P2 and have here P3, and I also have mu1 and here mu1, mu2, mu3, and here I have mu2. So those are my intensive variables, my generalized forces. The moment that I say to you equilibrium, okay, it's the same as saying, well, mu1 is exactly as mu2 and exactly as mu3. And P1 is exactly as P2 and exactly as P3. So any intensive variable or intensive force, it has to be the same across all the systems. Okay. I don't have the time to describe it to you, but we'll do it tomorrow to prove it. But what I'm saying is the following. I'll make the statement and prove it tomorrow. At equilibrium, the generalized forces are constant across the system. It doesn't matter what is my generalized force. You can invent some other variable and there is going to be an associated generalized force with this your variable. At equilibrium, it will always be exactly the same everywhere across your system. It doesn't mean there's going to be some small fluctuations, but it's going to be constant. This is something that is a very harsh condition that always applies to equilibrium. What it means that it's constant. So if there is a temperature T1 equals to T2, so this is the generalized force that it equals, what it means, when the temperatures are exactly the same, there is no flow of heat, right? Great. If the pressures P1 and P2 are exactly the same, the volume is going to be exactly the same because there is no modifications of volume, not of system A and not of system B. If the chemical potential is exactly the same in system A and system B, okay, there is not going to be what? Flow of particles from system A to system B. From time to time, maybe some particle will go from here to here, but also some particle will go from system B and system A. So the moment that you have constant forces across, or homogeneous forces across your whole system, the consequence is that no currents inside the system. at equilibrium, there is absolutely no current from any part of the system to any other part. What I mean by current, I mean systematic current. Right? There can be fluctuations. One particle from time to time can escape. There is some heat that can go from one part to another. But in general, no systematic currents inside the system. And we will show this. Right? The other thing we will show that it's actually not enough to establish equilibrium, because this is an outcome of the extremum of entropy. Okay? But there is something else that we have to consider. There was a question about this last week. Is this extremum is actually stable or not? Okay, so we will prove this concept tomorrow, and we'll also go into the concept of why the system are stable. We know that they are stable because we leave the system in equilibrium. It stays in equilibrium, but what it means to the generalized forces, the stability criteria. We'll see you all tomorrow. Thank you.
Thank you very much.
Hello.
Bye.